This is my circuit, and this is supposed to acquire the sound output from the stethoscope, which completes to be a biomedical signal processing system. I'll be using IC1A, which is ICT-L072 for stage 1. It is a dual low noise JFET input general purpose operational amplifier. It supplies voltage gain around 10 mV to 1 volt, but does not provide any current. The op-amp amplifies the sound where sound can be added or subtracted. Based on this circuit, it is a fixed gain closed-loop non-inverting op-amp, and the signal from the electric microphone needs to be brought up to a suitable level by the circuit for a line input. Capacitor C1 at 10 microfarads blocks the DC bias voltage from the input. At this part of the circuit, resistors R5 and R6 acts as a voltage divider, both at 10k ohms, and will provide half of the supply voltage, supplying the op-amp to work at a single supply mode. Therefore, I will get 4.5 volts. Resistors R2 and R3 and capacitors C2 and C3 will form a band-pass filter, which combines a low-pass and high-pass filter. A low-pass filter allows low frequency to pass through while attenuating high frequency, while high-pass filter allows high frequency to pass through while attenuating low frequency. This will cause the bandpass filter to allow only a specific band of frequency to pass through while rejecting all other frequencies. The formula for bandpass gain is 1 plus 220k ohms over 10k ohms, which is equal to 23. Capacitor C4 will act as a coupling capacitor, isolating DC signals and allowing AC signals to pass through. It couples the output IC1A, connecting it to the next segment. If any DC input offset were amplified, there will be a larger output offset, causing the output to be too large and reducing headroom. This will cause the waveform to be cut. These are my measurements for stage 1. As shown, as the frequency increases, the gain will also increase until it reaches around 23 at 100 Hz, and I got 24.8. The maximum frequency will be 100 Hz, as the gain of the frequencies above 100 Hz will drop. As I got 24.8 for the gain, I will be getting 27.9 decibels. On the frequency response curve, I will get 24.9 dB for the negative 3 dB line, as 27.9 dB minus 3 dB equals to 24.9 dB. By using a ruler and placing it at the 24.9 dB line, my low frequency will be 21 Hz, and the high frequency will be 1250 Hz. To find the bandwidth, the frequency will minus the low frequency to get 1229 Hz. The negative side of the waveform will be cut due to the single supply mode. To ensure that does not happen, The voltage divider, which is the level shifter, will shift the entire waveform upwards, causing the waveform to not be cut. For stage 2, IC1B shares the same ICT-L072 with IC1A. It is a negative feedback loop amplifier, where a portion of the output is subtracted from the input, returning back to the input with a phase inversion 180 degrees out of phase. Resistors R9 and R10 will be used as a voltage divider, each at 10k ohms. It is connected to pin 5 of IC1B. This allows the op-amp to work at a single supply mode and a level shifter to ensure the output will not be saturated. The feedback signal will then be controlled by trimmer P1, reducing the gain of the amplifier to not saturate the output voltage and act as a linear circuit. For stage 2, channel 1 is connected to TP2, while the frequency and power supply will remain the same as stage 1. Connect channel 2 to TP3, I will get 5.92 volts. Adjusting trimmer P1, the output waveform will be amplified, then become saturated, and be cut off at a certain point. At stage 3, IC2A is ICT-L072, the same as IC1A and IC1B. Capacitor C5 is 10 microfarads, will be a coupling capacitor, isolating DC signals and allowing AC signals to pass through. Resistors R11 and R12 will be the voltage divider, both at 10k ohms, acting as a single supply mode and a level shifter to ensure the output will not be saturated. IC2A is a Sallen-Key second-order low-pass filter, which is formed by using two low-pass RC networks. Capacitor C7 has 10 nanofarads, which provides this feedback for shaping the response near the edge of the pass band. This will allow the low frequency to pass through while filtering out the high frequency. The output voltage for IC2A will pass through capacitor C8, which is 10 microfarads. CA will filter out DC, acting as a coupling capacitor, allowing AC to pass through. Low frequency will be 0 Hz and the high frequency is the cutoff frequency. Bandwidth will be using the high frequency and minus the low frequency, giving me 996 Hz. Based on my recordings, the table will show that there will be unity gain in the beginning, but at 500 Hz, the gain and the output voltage will decrease. On the frequency response curve, to find the negative 3 dB line, I will use 0 minus 3 to get negative 3 dB. The high frequency is 999 Hz, thus the bandwidth will be 999 Hz minus 0 Hz, which is equals to 999 Hz. This is quite near to what I calculated. At the final stage, IC3 is LM386N-1. It's an audio amplifier. It is working in a single supply mode internally, which is why there is no need for a voltage divider. It will drive the current to the speaker to power it up. From TP4, the input will pass through trimmer P2 at pin E, which has full amplitude. Pin A and pin S have zero amplitude of the input waveform. C15 will filter out the high frequency above 40k ohms to ensure that the output waveforms remain stable. Capacitor C13 is a coupling capacitor which blocks DC signals and allows AC signals to pass through. At stage 4, channel 1 will be connected to TP4 and channel 2 will be connected to TP5. While everything will remain the same as stage 3, output voltage will be 8 volts. By adjusting the trimmer P2, output of TP5 will be saturated. The maximum sine wave attained without being saturated is the final output.